Borealis. So for you this evening, I'd like to introduce Colin Littlefield.
Thank you for that introduction, Gary. Now, before getting into the talk tonight, first of all, I'm just curious what people's level of experience or interest is in astronomy. Tonight's talk presumes no prior background, but I'm also interested to know if anyone perhaps has more of an in-depth background. And one of the reasons I ask that question is because one of the seasonal residents of Torrey, Gordon Myers, he is one of the world's most advanced amateur astronomers, someone I've actually collaborated with before on publications. And so you never know when there's going to be someone with just a ton of background in the audience. So anybody here, even just as an amateur astronomer? I see a couple of hands. It's hard for me to see through the lights in the back. So I want to reiterate that tonight's talk is non-technical. If at any point you feel like I'm glossing over something or I lapse into jargon, I would encourage you just to interrupt me mid-sentence. I would be happy to stop and explain whatever it was that I was glossing over. So the topic of my talk tonight is a star called T Coronae Borealis, which is probably one of the least interesting names you've ever heard, although it turns out that this star is actually it's actually pretty interesting, and it's been getting a lot of media attention for about the past 6 or 7 months because of a predicted eruption in the star that's going to happen, we think, sometime in the next couple of years. So my goal tonight is just going to be to give you an overview of what this star is like, kind of the general physics behind it without getting into any technical stuff, thankfully. And then kind of explaining what you can expect later in the year or next year when it's expected to erupt, because it's something you'll be able to see just with the unaided eye, especially from a community with the pristine skies of Torrey. Next slide, please. So we're going to get to T Coronae, as it's known by most astronomers, in a minute. But first, I want to give an overview of what it is about T Coronae that's going to produce this eruption, we think. So I refer to T Coronae as a star, and that's actually a little bit misleading because it turns out that even though we see one star when we look at it through a telescope, it's actually 2 stars. And one of them is called a white dwarf. And this is what is going to be responsible for that spectacular eruption that's been predicted for some time in the next couple of years. So a white dwarf is essentially the burned out core of a star that used to be like the sun. So it's an ancient object. If you could go back in time billions of years to see what it looked like back then, it would likely resemble our own sun, probably a little bit bigger and hotter. But overall, it would be very similar. And now all that's left is this tiny Earth-sized remnant that contains about the mass of the sun, except it's in an extremely small volume of space. So white dwarfs are famous for just being extremely dense, that you could take just a teaspoon of white dwarf material, and if you could weigh it on Earth, it would be many tons. And so the entire star is just unimaginably dense by our everyday standards. And one of the interesting things about white dwarfs, and this ties in with one of my research interests, is that if they happen to be close to a normal star, they can actually rip material off of that second star and capture it. And so the material will approach the white dwarf and eventually land on it. So we call this process mass transfer because this normal star is losing mass and transferring it onto the white dwarf. So this is one of the key ingredients to this nova eruption that I've been talking about. Next slide, please. So when a white dwarf is close to a normal star and it's able to siphon mass off of it, we call that a cataclysmic variable star, one of my research interests over the years. And so I found a fairly useful kind of schematic of what a cataclysmic variable will look like. courtesy of NASA. So you'll have this normal star, and you get that tiny, you'll notice it's distorted from being spherical into a teardrop shape. And at the tip of the teardrop, you can see a little stream of mass that encounters this giant disk. We call it an accretion disk, but that bit of jargon is not important. Once the material is in this disk, it'll slowly spiral in until it's able to reach the white dwarf, and at that point, it just piles onto the white dwarf and makes the white dwarf a little bit more massive. And then this process leads to a number of really, what I consider to be really exotic events that will happen, because sometimes that disk will just, it'll en masse, it'll just collapse onto the white dwarf during something we call an outburst. And then there's something even more exotic that can happen called a nova, which is what will be happening in T Coronae. I'll get to the specifics of the nova eruption in a couple of slides. But first I've got what I consider to be a useful animation that I found online to show you what a cataclysmic variable looks like. I think it looks a little bit more interesting than that slide there. So just bear with me for one moment while I do the switch. I think you can see why I prefer this to just the static figure. I wish that I had this level of skill to create an animation like that, but sadly I don't. So the main takeaways here would be that distorted normal star. Oh. And then could you pause it when it reaches the end? So the main takeaways here would be that you have that normal star, which is distorted by the white dwarf's gravity into that teardrop shape. And then that stream of mass that's being transferred into that disk that orbits the white dwarf, and where the material in the disk is slowly spiraling in until it lands on the white dwarf. So this is actually a pretty reasonably accurate representation of what T Coronae would look like if you could travel all the way there. There's some differences, but I don't consider them to be terribly important for our purposes tonight. So we're dealing with T Coronae. We're dealing with two stars, the white dwarf there that's gaining mass from a fairly normal companion star called a red giant. The reason it's called a red giant, I think you can guess from this the reason we call it red. It's the temperature of the star that gives it a red hue to it. We call it a giant star because it's about 75 times the radius of our sun. So just think about that for a second. The two stars in T Coronae, one of them is about 1% the size of the sun. The other is 75 times larger than the sun. So it's a really interesting contrast and extremes there. I see a hand in the front row.
Are there any planets involved in the area of these two stars?
The question was whether there are any planets involved in the area of these two stars. And the answer to that, I guess there are two answers. The first would be that we haven't detected any evidence yet, one way or the other. From a more theoretical standpoint, it would seem, I suppose, unlikely, because when that white dwarf, if you think about what it was like billions of years ago, when it was a normal star, it reached the end of its life, and it expanded outwards and formed a red giant of its own, and eventually it ejected those layers out into interstellar space, and that would be a difficult environment for a planetary system. It's possible that there are still some remnants of planets in that system, but the problem is that red giant star is so bright and so large that it makes all of our conventional techniques of detecting planets around other stars, it makes them fail. Because normally when we're looking for planets around other stars, we try to target stars that are fairly small for a variety of reasons. And if you're looking at a red giant, it's really tough to be able to detect planets in that environment.
So, one more, if you don't mind. Was this other star just wandering by and got caught into this situation?
The question was the red giant, the star that we currently see as the red giant, was that just wandering by and it got caught into the situation? And the answer is no. Every model of cataclysmic variable stars predicts that these stars were formed together out of the same cloud of gas and dust that collapsed into the stars. But billions of years ago, they would have been much farther apart, and they would have both appeared somewhat like our own sun, rather than this extreme situation today where one is a red giant, 75 times larger than the sun, and the other is a white dwarf, less than 1% the size of the sun.
So, short technical note, if anyone has a question to ask, please come to the microphone here. We forgot to make that announcement beforehand. We stream and record these, so it makes it a lot easier if our audience outside this room can hear the question.
I'm also happy to just repeat the question.
I would prefer people to come to the microphone.
Okay. I'm going to switch back to my presentation.
We have a question over here. I have a question.
So I mentioned, I'm sorry, go ahead. I see a question.
So why is the material from the red giant from a disk rather than a sphere?
So the question for anyone who didn't hear it was, why does the material from the red giant form a disk rather than a sphere? And the answer to that is because it has what in physics we would call the angular momentum of the star. Essentially, what that means in practice is that it constrains where that material, the direction that material can travel after it leaves the red giant. So if you're just in everyday experience, you might be familiar with the concept of momentum. Say you're driving your car, you build up some speed and you take your foot off the gas. The car is going to keep moving. It's not going to change directions unless you turn the wheel or something. There's some other unfortunate incident that happens. You blow a tire or something, that would change your direction too. But the bottom line is that absent some outside force, it's just going to keep going in the direction that it's going. So the material after it leaves the red giant is going to maintain its momentum, but it's also being tugged on by the gravity of the white dwarf. And so that curves its path and forces it to form a disk-shaped structure rather than a spherical structure. Because if you wanted a sphere, you'd have to be able to give it a push either vertically or down in order to move it out of what would otherwise be its path. So I mentioned with T Coronae that there are several, and cataclysmic variable stars more generally, there are several really interesting types of eruptions that they can undergo from time to time. And the one that's relevant to T Coronae in this nova eruption, it's powered by a process called nuclear fusion, which I think a lot of you may have heard, but in entirely different contexts before. Perhaps you've heard about it as a possible source of green energy in the future. Maybe you've heard about it as a way to make thermonuclear weapons even more destructive. We see it all over the place in astronomy, nuclear fusion that is. It's the process that powers stars. And in cataclysmic variable stars, it's the process that powers something called novae. So for those of you who haven't who might want a refresher, I've included just this graphic here. Don't worry about the numbers on it. Just think of it as kind of a schematic showing what happens during one particular type of nuclear reaction. That you start out with two isotopes of hydrogen up here, deuterium and tritium. You slam them together, and to do that, you need extraordinarily high pressures that you don't encounter in everyday life on Earth. You need a really exotic environment to be able to achieve those pressures. So, for example, the core of a star is one place where you have sufficient pressure to fuse elements. And the net result of fusing those two isotopes of hydrogen is that you're left with a helium nucleus, which is heavier. And if you add up the mass of those two hydrogen isotopes and you compare it with the mass of the helium nucleus that you get afterwards, you'll find that a little bit of that mass has disappeared, and it's been converted directly into energy via Einstein's famous equation, E equals mc squared. So what's happening with fusion is you take lighter elements, usually hydrogen, you slam them together at extraordinarily high pressures, and you get heavier elements like helium and also some energy. And that's the process that powers stars and also nova eruptions, which I'll finally explain on the next slide. So a nova eruption occurs when you have a layer of hydrogen on a white dwarf and it experiences runaway nuclear fusion. So you have hydrogen that's been stolen from that red giant, and eventually the pressure builds up to the point where the hydrogen is able to fuse into heavier elements. And this is an extraordinarily energetic process. You can think of it almost as a hydrogen bomb that's exploding over the entire surface of the star. It's kind of a crude analogy, but I think reasonably accurate. And so when this happens, as you might imagine, there's a lot of energy released, and we see the star brighten very dramatically in visible light. So T Coronae is normally quite faint, and you would need a small telescope to see it. But when it undergoes its nova eruption, it's going to brighten to the point where it'll be very easy to see with the naked eye. And then the aftermath of the nova eruption is that material that underwent fusion on the surface of the white dwarf, it's going to be expelled outwards into interstellar space, and we'll see something like this called a nova remnant. So in this case, I've taken 3 different stars that experienced nova eruptions, courtesy of this paper over here. And I'm showing one of their figures where they actually detected the expansion of one of those remnants of a nova. And so this is just that gas that's been expelled from the white dwarf and is expanding outwards into interstellar space. And so what happens is that eventually those shells will fade away and dissipate. But they're one of the ways that you can test whether a particular star has experienced a nova fairly recently, within the past few centuries. So there have been times where perhaps ancient astronomers couldn't have detected a particular nova, but we can go back now and we can detect these expanding shells around them, and we can determine that, okay, this star had a nova eruption perhaps a few centuries ago. Next slide, please. So finally, now that all the background is out of the way, I'd like to shift gears and talk specifically about T Coronae. So T Coronae is what we call a recurrent nova. So in other systems, so in other cataclysmic variable stars, we expect there to be a nova eruption every 10,000 years, maybe 100,000 years. It's a very long interval, and we've only been doing astronomy on Earth for a few thousand years at most, if you count what ancient astronomers were able to do just with naked eye observations. So we obviously don't have enough data to test whether novae really do reoccur every 100,000 years or so. What sets T Coronae apart is that it has nova eruptions every 80 years. And there have now been 3 that have been observed, I think, pretty convincingly. So two nova eruptions in T Coronae, absolutely no question that they happened. And I've listed their years up here, 1866 and 1946. It turns out that there's some reports of possible eruptions from T Coronae even before that. So there's a fairly well-regarded astronomer in 1787 who reported apparently a new star in the vicinity of T Coronae. And there was an interesting paper by an astrophysicist who specializes in novae. And he was able to look at what that star might have been that was spotted in 1787. And he considered all the possible explanations. And his conclusion was that it could only have been a nova eruption by T Coronae. And if you do the numbers where it's 80 years between eruptions, approximately 80 years, that works out too. So there's also a report, and this one I consider to be much more ambiguous, a report by German monks in the year 1217. This one I read the argument that it could have been T Coronae, and I think it probably was, but it's much more of an ambiguous case. So I wouldn't claim that one as a definite prior observation of one of these novae. So one other thing I'll just point out in terms of how much fuel is ignited, it's about 1/3 of the mass of the Earth that participates in this process. So why are we so confident that T Coronae is going to go off in the next couple of years? Because I've said that several times now, and I haven't actually done anything to prove it to you, other than the fact that we're about 80 years after the most recent nova eruption. Next slide, please. So I've adapted here a figure from what I consider to be probably the authoritative paper on this question. So I know there's a lot going on here, but let me explain. These green points that you see are measurements that are made in green light. They're supposed to approximate the sensitivity of the human eye. So in fact, a lot of these early observations that you see from the 1800s, those were just people visually looking at T Coronae with, say, a telescope and estimating how bright it was. These blue measurements, which are more recent, are derived from, so first of all, they're more sensitive to blue light. That's why they're color-coded as such. A lot of them are derived from photographic plates right after that technology was developed in the late 19th century. And then more recently, these are digital measurements using a detector that's observing through a blue filter. So kind of the simplified way of thinking about this is that this is how bright T Coronae is in green light, and these blue points are how bright it is in blue light. And to give you an idea of the scale here, because I deliberately removed that to make the jargon a little less problematic. Up here, when T Coronae is at its peak brightness, everything above this line that I'm drawing is about naked eye brightness. So you can see that for most of that 80-year cycle, T Coronae is way below naked eye brightness, and then it just barely, just for a week or two, it'll surge above that, and then it will fade really quickly. So most of T Coronae's lifespan is spent in this faint state. Now, around the 1946 nova outburst, so that would be this line here, where it skyrockets and then fades. There's an interesting feature here. It's this plateau that you see around the nova. So you'll notice that several years before, particularly in blue light, it suddenly starts to brighten, and then it levels off, and then it drops down, and then all of a sudden you have the nova eruption. And this was seen, although not nearly as clearly, in the first event in 1866. And getting over to more recent times, so here's where we are now, and you can see that plateau starting again. Could you go to the next slide, please? So this is an enlargement of that area that I had circled on the previous slide. So the purple line here is the author's, when I say the author, a man by the name of Brad Schaefer, a specialist in novae. This purple line is kind of a model of the 1946 nova eruption. And he's overlaying it here with the recent observations of T Coronae. And you'll notice that, first of all, it's not a perfect fit, but it does generally reproduce the observations that we see. It does a pretty decent job of predicting it. And it's on this basis that Schaefer predicts that sometime in 2025 or 2026, at the latest, we'll likely see a nova eruption. Now, he also did predict it could occur as early as this year, but the most recent observations don't show that really distinctive dip right there where it suddenly fades right before the nova eruption. So I have a feeling it's probably not going to happen this year, although I would absolutely love to be proven wrong on that point. So in particular, you'll notice that T Coronae hasn't reached the same brightness as it did in the 1946 event. And Schaefer has discussed the possibility that this might mean that it's still going to be a little while longer before we get to the nova eruption. And there was another paper, too, that made kind of a similar argument, predicting that it might be more like 2025 to 2026 rather than this year, as a lot of the media, unfortunately, has really been hyping up. Could we go to the next slide, please? So I'd like to, kind of as we approach the end of this talk, I'd like to focus a little bit just on what the actual nova eruption will be like, because this is something that I think when it happens, there's going to be a lot of media coverage of it, and it's going to be the big thing that everyone wants to go out and look at. So I scoured the internet trying to see if anyone had simulated what it might appear like. And I was kind of disappointed. I only found this one slide, or this one picture. It's a synthetic one, as you might imagine, prepared by George Washington University, showing T Coronae as an extremely bright star. So this curved constellation that you see here is called Coronae Borealis. That's the Coronae part of the star's name. And here we see that T Coronae is being depicted as this brilliant star that outshines everything in the vicinity. And here again, I would be very, very happy if it were this bright, but I don't think it's going to be. Again, I'd want to be proven wrong, though. Realistically, if you compare how bright T Coronae was in its previous nova eruptions, it'll be more like this star right here. So you'd be looking at this patch of the sky one night before the nova eruption. You wouldn't see anything there, and then the next night you'd see a star of about this brightness. So it would probably be in about the top 50 stars ranked by brightness in the night sky. But that's not a very impressive statement. It would be one star amongst many. So experienced amateur astronomers would probably just look at the constellation Coronae Borealis, and they'd instantly spot it because it would just look completely wrong to have that star there. But if you're just kind of casually interested in astronomy and maybe you're not as familiar with the constellations, this nova would not jump out at you. You'd definitely need an app on your phone or just like a printed star map in order to be able to pick it out. Could you go to the next slide? I think that should be, yep, this is the last one. So this one is a little bit speculative, but it's kind of tying in the relevance of these recurring novae to the overall fate of T Coronae. So the white dwarf that I mentioned in T Coronae is extremely, extremely massive. In fact, so much so that it's very close to the upper limit for how massive a white dwarf can be without exploding as a supernova. So a supernova is where the entire white dwarf explodes catastrophically. It does not survive that event, whereas a nova eruption, it's just this tiny atmosphere on the white dwarf that undergoes the eruption. So a supernova would be the end of T Coronae as we know it. And what will happen with this mass transfer process is that the white dwarf, in principle, could get so heavy that it will reach that upper limit, at which point it would explode, the entire star. And this is an area where astronomers are really interested in measuring the upcoming nova, because there have been some contrarian astronomers who have said that the nova process will actually cause the white dwarf to get a little bit lighter. Because you might remember I showed you a slide earlier where there was a shell of gas expanding after the nova, carrying away some of the white dwarf's mass. So the big question is, with each cycle of these nova eruptions, does the white dwarf get heavier afterwards, or does it get a little bit lighter? If it gets lighter, it's not going to explode as a supernova. If it continues to get heavier, there's an extremely good chance that it would. And if it did explode as a supernova, that would be an event where you would be able to see it in broad daylight on Earth because it's so close. Supernovae are some of the most energetic and brightest events in the entire universe. They can literally be seen across the observable universe. And certainly a nearby supernova that you could see in broad daylight, I think that's probably the dream of most observational astronomers. We're overdue for one. So just to quickly explain the different scaling here. So this would be T Coronae as it exists now. And then this is what it would be after it explodes as a supernova. But there's a very different scale here. So you'll see 20 days after the explosion, 50 astronomical units. 1 astronomical unit is about 100 million miles. I'm rounding there. It's about the average distance from the Earth to the Sun. So this shell that you see here would be absolutely massive because of the huge ejection velocities in a supernova explosion, as all the remnants of that star just get blasted out into interstellar space. So that will be one of the main, I think, scientific objectives of this forthcoming nova eruption, to see if this might be the future fate of T Coronae. And I believe that should be the last slide. I'd be happy to take any questions.
How long do you think the supernova will be visible, or not super, the nova be visible from Earth?
Probably a matter of days, maybe a couple of weeks. So it fades really quickly. You'll be able to follow it with a telescope much longer. But in terms of just the naked eye visibility, I probably would limit my estimate to a few days.
What's the distance to
It's about 3,000 light years away. So we see it as it appeared 3,000 years ago. Another way of thinking about that is that this much heralded nova eruption that I've been talking about, it's already happened. It's just a matter of when that light is finally going to reach the Earth. In fact, many more of those nova eruptions have already happened, and the light is traveling towards Earth as we speak. So astronomers have a very strange way of naming stars. Stars that change in brightness are known as variable stars, and they have their own special nomenclature. And T Coronae very clearly is a star that changes in brightness because it's faint most of the time, and then for a few weeks it'll be bright enough to see with the naked eye, and then it'll fade again. So the way that variable star nomenclature works is that you take the name of the constellation and then you put a letter before it. I think the letter indicates the order in which it was observed, or excuse me, the order in which it was discovered. And they started out with single letters, and after they ran out of single letters, they started doing double letters. And after they ran out of double letters, they changed it to V followed by a number. It's confusing. One of the tricks you learn in astronomy is when you come across some of those obscure names, you try not to think too hard about it because it'll give you a headache pretty quickly.
You said the supernova would be visible in broad daylight. What kind of shape is it?
It would look like a bright star. So I think the most famous predecessor of this would have been a supernova that was observed in the year 1064, I think. It was observed in broad daylight by Chinese astronomers who recorded its position. And then almost a millennium later, astronomers were actually able to match up the star that they observed during broad daylight with something that we call the Crab Nebula. It's the exploded remnants of the star that the Chinese astronomers saw go supernova in 1064. And you can see that the Crab Nebula is still expanding outwards. And if you measure the rate at which it's expanding, you can calculate the time when it exploded, and it matches up perfectly with the date that the Chinese astronomers observed it. I mean, just kind of mind-boggling to think that when they recorded the star's position, they probably had no idea that almost a millennium later that astronomers would be able to make this incredible discovery based on their observations.
Will it have enough mass? If there's a supernova, will it have enough mass to turn into a big
Yes. Well, so this is a special type of supernova called a the jargony name of the supernova isn't important. This particular supernova, when a white dwarf explodes, it does not leave behind either a neutron star or a black hole. There's no remnant. If you want a supernova that will leave behind a remnant, you need an extremely massive star, because otherwise, just with an exploding white dwarf, there's nothing left behind afterwards.
Will there be a black hole?
Eventually, so a black dwarf is a white dwarf that has cooled so much that it no longer has any appreciable temperature. It's close to absolute zero, the coldest temperature that's possible in the universe. All white dwarfs are expected to eventually become black dwarfs, but there's a big caveat there. They cool off really, really, really slowly. So the answer is yes, eventually, but it's probably going to be in billions or even trillions of years, much, much longer than the current age of the universe. It's always a pleasure to see someone young who's really interested in astronomy. Those are good questions. Anybody else?
In the first drawings, you saw the large star was just drawing off pieces.
Why didn't you just take it all at once?
So there are actually a number of unresolved questions with T Coronae. So I have a couple of comments about that. The first one would be that, actually, if you could go back several slides, I'll tell you when to stop. Yes, this one. So this plateau that astronomers are so excited about, that we think is the harbinger of an upcoming nova eruption. One of the questions is, why does it get this bright around the time of the nova and then fade again? We think that this has to do with how much mass is being transferred from that red giant onto the white dwarf. But that doesn't really explain why would we see the amount of mass increase every 80 years. We don't know really of any cycles in the red giant that could cause it to suddenly increase the amount of mass that it's sending to the white dwarf. So, Gary, if your question is why is the amount of mass that's being transferred, why is that highly variable? The short answer is we don't really know, but we would certainly like to. So with all the modern equipment that's been developed in the past 80 years, I think there are going to probably be some interesting papers that come out on that subject.